on Friday afternoon to join Jamie and I on what we hope will be an interesting and informative discussion. And the idea here is to talk to you about how do you actually go about building a microgrid, which is what I'll focus on, more on the business, on the technical aspects. And then I'll turn it over to my colleague Jamie, who will focus more on the permitting aspect, especially in the state of California, other areas. I'll turn to Jamie. Jamie, do you want to say something?
Yes, hi. Good afternoon. Jamie Schnick. I work for the state of California at the Office of Statewide Health and Planning, otherwise known as OSHPD. I've been an engineer for 30 years and just started at OSHPD second year. Excited to talk about microgrid.
Very good. Thank you. So can we get the presentation on? There you go. Let's get it on full screen. All right. So I'm Suresh Jambanathan, and I'm the founder of Energy and Water Development, which is a small boutique consulting development firm in the Chicago area. The agenda is like so. As the first speaker, I'll talk for about 20 minutes on microgrids with a technical business focus, turn it over to Jamie, and then we will have a Q&A session. Highly recommend ask for questions. Nothing worse than just talking to an empty screen or an open empty room. We'll first talk about microgrids, what, why, and how. Talk a little bit about the sustainability benefits. Many people have heard about that. And then really get to the heart of it, which is how do you actually develop a microgrid from literally pencil to paper all the way to project development, financing, construction, operations, maintenance. Who's Energy Water Development? We are what I would call an ABC firm. A is the consulting part, where we give advice, hopefully in exchange for money. B is the development part, where you actually take the advice and actually build something, building the project. And that can take multiple streams that we'll talk about. And third, C, is the operations and maintenance. The fun part is the consulting and the development. The boring part of the O&M, that's the most crucial to maintain the project value over the life of the project. I would ask you to look at the assertions, which are really axiomatic, self-evident, but really important. We can be good and we can be green. And profitability actually goes hand in hand with sustainability. From high-level context, next couple of slides, especially for those who might be unfamiliar with the concept of a microgrid. A microgrid is basically a bonsai version, a mini version of the regular grid. The regular grid consists of multiple generation units, coal plants, nuclear plants, renewable power, wind, sun, hydro, so on. And then all that output goes into use points across transmission wires and is used. A microgrid is just the same thing in a much smaller geography. It could be as small as one house, could be as small as a factory or industrial complex. You may have one or two generation units when the power and the heat, in some cases water treatment, is used by the people in that area. A defining feature is you can electrically disconnect, almost like flipping on, flipping off a switch, the microgrid from the larger grid. Microgrids are not new. As with most things, people like to throw jargon around, but the first microgrid actually predates our current, what is called remote grid. The first microgrid was done by Thomas Edison back in the 1870s at the Pearl Street Generation Station. He burned coal, and he made steam, and he made power. He ran the high pressure steam through a back pressure steam turbine, which is an example of a generating unit. And then that power lit a few houses in the neighborhood. So that was actually the very first microgrid. Microgrids can come in various shapes and forms and flavors. This slide is sort of helpful to get a high-level overview of the building blocks of a microgrid. The building blocks of a microgrid can be what is called the prime mover. And I'm assuming in this particular, for purpose of this discussion, I'm using a prime mover, meaning an engine or a gas turbine. A gas turbine is a jet engine. And an engine is basically a car engine, just an oversized car engine, as an example of the prime mover. So you either burn fuel or run steam through it, make some power. the waste heat can be recaptured, reused. That is an example of what's called a combined heat and power, which is a building block of a microgrid. When you layer on renewable energy, wind and sun, it gets interesting because wind and sun, renewable energy is fuel-free, but it is highly intermittent and variable. Hence, one of the challenges of keeping the microgrid supply steady, you can either put a battery or a fancy controller or some combination of both. It all comes down to economics. The technical stuff is actually pretty well understood. What's the high-level benefit? Again, it's pretty straightforward. You're more efficient. You get more miles per gallon, which means your cost is reduced, and that has sustainable benefits. A picture is worth 1,000 words. So the above picture is a CHP at the University of Massachusetts in Amherst. You can see all the energy, the fuel is spoken for as power and heat. The picture in the bottom one is a typical coal plant, and all that water vapor is literally thermal energy, waste heat being thrown away. Just about 1/3 of the energy in the fuel becomes electricity. 2/3 is literally thrown up in the air like that. And that's really in economic waste. It also throws up carbon dioxide, which is a separate issue. Okay, so that was sort of the background, and I hope you found that helpful. Let's talk a little bit about, the high-level questions. The most important, do I want or need a microgrid? How do you build it? How do you operate, maintain it? Again, ABC. The first question on, do I want or need a microgrid? Always starts with the basics. What is the objective? It's like buying a house. You can buy a hut or you can buy a mansion. When you say, I want a microgrid, set the objective. Putting the objectives clearly is half the battle. Then gathering data. Then you come up with alternate conceptual configurations and the corresponding economics. That's the consulting part. And then you get into the nuts and bolts of project development. And it's helpful to think of project development as having multiple parallel streams. There's a technical stream, there's a legal, commercial, environmental, financial, very important. And of course, risk and mitigants. Good project development is all about mitigating risk. And no matter what happens on paper, in real life, something or other seems to go wrong. And a good plan mitigates those risks in operations. Okay. Now let's take a second look at this very interesting slide, which is, microgrid is great, but then peanut butter and jelly sandwich is also great. The question is, do you need a microgrid? Who is it important to? The people who are involved, how might they view a microgrid? If it's a company and you're the CEO of the board, their view of a microgrid is a more strategic view. Does it increase shareholder value? Does it show to the world that we are green and we are actually also adding cash to the bottom line? The chief financial officer or the financial group, they are more concerned about, does it improve operating cash flow? Does it increase enterprise value? The operations staff are more concerned about, does it improve or does it decrease site availability? Does it increase resiliency? If you're a grid manager, you want to make sure the microgrid doesn't blow the whole grid up, have a kind of frequency spike, for instance, in either direction. If a regulator, you want to make sure that the public interest is protected, that you're not burning coal and spewing all sort of nasty stuff into the atmosphere. And the community. At the end of the day, the business exists to serve the community, so whatever is done should be good for the community. And so, if you take a step back, once you think about, does this make economic sense? Does it make social sense? And the two actually go together. So, from the 100,000 foot to the 50,000 foot, now we're getting down to the 25,000 foot level. We sort of decided a microgrid makes sense, we want to build it. Well, how do we get started? Always, I put the picture of the monkey there because thinking is hard work. People put a lot of effort to avoid the effort of thinking. And it's really, really important. Let me repeat that. People put a lot of effort to avoid the effort of thinking. A good project starts with a lot of thinking. It's a lot of iterative effort. And it starts with what's really important and what needs to be done. And that the list under thought and actions are some of the things one should think about, sketch out, review again, discuss, debate, till all the cobwebs in the mind are sorted out. Okay, now we're getting down to the nuts and bolts. The first step is, once you decided, look, I need a microgrid, it sort of makes sense for so many reasons. The nuts and bolts will start with what is called the load profile. how much power, how much thermal energy. Thermal energy can be heating or chilling that you need. And it starts by just graphing the load per day, per hour, per year. Then you take paper and pencil. Nowadays, people use software. It doesn't really matter. The important thing is to actually put something on paper, a solution that directionally starts to meet the load. And as you do it, it's an iterative process, because along with the load sketching, the load graphing, and the concept development, you also have to ask yourself, look, is this going to be a Taj Mahal, or is it going to be a Ford? No, 150, and I like Ford 150s, by the way. That's as rugged and stable, and it runs on and on and on. Part of the sketching process is to really put paper and pencil, or in many cases software, just sketch out the entire process design, including the elements of financial model. Really important, get buy-in from people. Say, hey, are we missing something? Oftentimes, you ask a question, you get 10 questions back. But that's a very rewarding exercise, saves a lot of grief later on. Once you've done that, pick a design or two, start sizing it. Sizing means you create what is called a mass and energy balance. Anything going in has to come out the other side. The rate at which it goes in and comes out determines the size of the equipment. Once you do that, you can start shifting more towards things like, what are the emissions going to be? What's the capital cost going to be? What are the operational risks? How do we mitigate it? So on and so forth. I talked about the fact that good project development is all about having a robust project execution plan. And because a project like a microgrid has a technical component, a financial, legal, commercial, permitting, so on and so forth, it's really important to know where you are and to get to where you want to go. Sort of chalk out the key steps. And then graphing that helps to figure out what is the critical path. Where is there flex? Where are we underestimating or overestimating something? It's a good way to make sure that one is not over-promising and under-delivering, or rather, instead do the reverse, under-promise and over-deliver. Capital budgeting. All this technical stuff is great. It's all fun and games until it comes down to the money. Somebody is going to ask very quickly ask the question, okay, all this is great. What's it going to cost? To answer the what's it going to cost question, you need to have some sort of a process design, a sketch, a schematic, a drawing is good. Based on that, you say, look, I need these pots and pans, the engine here, battery there, thermal storage unit there, the electrical switchgear here. All these pots and pans that I need to buy or get is going to cost so much. Once you do all of that, you have a indicative cost. But it's important to recognize at the early stage of project development, there's a lot of uncertainty to all the different cost items. Hence, I would highly recommend using what is called an uncertainty adjusted estimate, where for each line item, you just add some uncertainty, add it up. The number at the bottom right is typically the not to exceed number for the project. Financial model. Once you have the capital cost, create a financial model. A discounted cash flow analysis is a good way to do that. Along with the financial model, it helps to start recognizing what are the key project risks. Is it technical risk? Is it financial risk? Is it exchange rate risk? Is it operational risk? Permitting risk? Risk can be multiple categories. Important to list them all out and very dispassionately ask, how are we going to mitigate the risk? And if things go the wrong way, who's left holding the bag? Really, really important. The heart of project development, closing the deal, is proper risk identification and risk mitigation. Economic sensitivity, pretty straightforward. It's one thing to say, I'll make a fortune on paper. It's important to ask the question, if the price of power or the cost of fuel or the people's salaries or inflation or whatever it is goes up, down, sideways, what happens? A good economic model with a good sensitivity analysis bounds the financial risk of a project. Okay, I kind of talked about this, but it's helpful to look at this again. Trade-offs. When you're starting a project, early conversations, all the estimates are order of magnitude. So when someone says, I think it's going to cost $20 million, that number could be 15, it could be 25. It could even be 10, depending on whether the guys had 1 beer or 5 beers. And it's only after spending a little bit of time, money, and effort defining the project does the uncertainty on the project estimate, which is the capital cost, the delivery time, the performance, etc., start to narrow. And it's pretty common sense when you think about it. Early on, it's all over the place. As you spend time, money, and effort, the estimates improve. So it's a question of where you are on that curve. The front-end loading is a very common method used by engineering companies to manage a project. It's basically what is called a stage gate process. There's another acronym called FEED, front-end engineering design, but it helps to think of a FEL as, where are we in the project? Most cases, when you're looking at multiple ideas, you do what is called a FEL1, a business assessment. If it passes the sniff test, that's the business assessment, then you say, look, I think there's enough potential here, and the risks seem manageable enough that we should go further. And as you go from left to right, that's essentially going down the path of project development. And it's very helpful to stare at this diagram and internalize that and understand what stage of project we are at. So now, let's talk a little bit about contracting strategy and risk mitigation. For larger projects, if it's a small project, it could just be a capital expenditure in the company. Go to the financial department, put in a requisition, they'll write a check, you buy it, there you go. As the projects get larger, more complex, more non-core to the company. If you're a hospital, your goal is to get the sick patients in and the healthy patients out, not necessarily in the power and water generation business. In that case, it might make sense to work with a project developer. And a good way to create a project is what is called a project special purpose vehicle. That special purpose vehicle becomes a legal entity that then contracts with everybody to deliver the project. The contracting counterparties are the boxes around the center of that box. A good contract should be really simple, and I'm a firm believer that if you cannot explain something on a sheet of paper or about 2 minutes or in 5 sentences, then you, the guy who's trying to do the explaining, doesn't really know what he's talking about. So when it comes to pricing, a simple pricing is always better than a complex pricing mechanism, because the latter inevitably will lead to lawsuits down the line when something goes wrong. Okay, so talked about the A and the B, which is designing and building a microgrid. But now, how about operating and maintaining it? Okay. If you take a step back and sort of take a philosophical look at it, in the United States today, we are such a prosperous country because we generally have a free market system. And the free market system does have a couple of issues, legitimate issues one can, poke holes in. But generally, it's a great wealth creation machine, spreads wealth to a lot of people. But the idea of a free market is not new. It's in fact very, very, from when human civilization started. In India, there's Chanakya, who essentially advised a laissez-faire free market economy, and so did Adam Smith. And Adam Smith's book, The Wealth of Nations, is a foundational text of economics in the modern world, at least the modern Western world. And the core here is, go back here. Oops. The core insight is, one should focus on the core competence and outsource the non-core needs. And a microgrid is essential, but it's non-core to the business. So operation maintenance, again, it's fairly straightforward. If you do proper housekeeping, keep things clean, and maintain things as they should, change the oil when you should, you prevent problems down the line. How do you actually get that done? Your training. An emphasis on safety is really important, and following recommended procedures, redundancy, so that when something goes wrong, you have a backup unit. Things like that are really important. It's not rocket science. It's really a matter of deciding what you have, deciding how you're going to operate and maintain the system, making sure you're well-staffed, well-resourced, the staff you have are properly trained. If not, either train them or get the skills, so on and so forth. For maintenance, it's always good to have a set of critical spares, maybe some more as-needed spares on the shelf. That means you are adding to the working capital or capital budget, but it improves your overall availability, which is a good thing. O&M structures, you can have a full soup to nuts coverage, or you can have just a basic inspection. It's really, you get what you pay for. If you don't want any headache, you get full soup to nuts coverage. If you're very comfortable doing some of the maintenance yourself, it might make sense to have only specialized maintenance. Just change the oil yourself as an example. But when there's a major brake change, or I'm using a car as an analogy, but if you need to change the brakes or do a transmission overhaul, get somebody else to do it. or just change the oil yourself, or have someone do the whole thing completely. So with that, I will conclude my presentation, and I will turn it over to my colleague Jamie. When Jamie is done, we would welcome some Q&A. Jamie, over to you.
Thank you, Suresh. So in California, I was involved in putting together a white paper called Microgrids for Healthcare Facilities. And you'll see a link to that at the end of this presentation, and that's what I'll be talking about. Next slide. Next, yeah. So what is a microgrid? I think Suresh talked about it a little bit, but in general, it's a combination of equipment that produces energy and delivers power, and it's located on the site of the facility. We're talking healthcare facilities here, so this would be on the hospital campus. As power generators, it could use combined heat and power systems, turbines and generators, photovoltaics, fuel cells, wind, geothermal, any combination of these energy producers. Next slide. Why? In California, we've always had the threat of earthquakes. But in the last decade, we've also encountered a new threat, and that is the wildfires. As a result of the wildfires that have taken place and all the destruction, utility companies have what they call a public safety power shutoffs. And we're guaranteed pretty much to have a number of those each year. And those power shutoffs will render the resident without power for multiple days at a time. And so microgrids provide an opportunity to continue to power your facility during these utility grid shutdowns. Some of the benefits: increased power reliability. If you use green energy producers, lower environmental impacts, lower energy costs. You're able to use these microgrids to work with the utility company and peak shave and control the cost of your energy, and then potentially higher power. Next slide, please. As a regulatory agency, I was involved in putting together the paper for codes and standards. So I'm going to talk about three major categories of compliance. Number one, there's requirements for connecting with the utility. Number two, there are air permits in California. And number three, there are building permits. Next slide, please. You'll see here all, but as I said, the white paper you can get a hold of, and we'll have this. I've listed 18 applicable codes that could come into play for implementing a microgrid. And it's actually 30 line items because it's different articles of the codes. And it talks about, CARB, who manages the Air Resource Board in California, the CPUC, which is the utility company, and then a number of codes talking about generators, fuel cells, microgrids, fuel storage. So we can go to the next slide, please. First, we'll talk about Rule 21, which is the public utility. Essentially, the public utility will need to approve all designs that implement microgrids that parallel with their utility service. It has been in the past a big effort, fairly challenging on projects to get this worked out. Essentially, they need to guarantee the safety of their grid. And typically their requirement is that you do not backfeed the grid with your on-site microgrid. It's a safety thing. We move on. Next slide. Air permits. In California, the California Air Resource Board is the state agency that regulates the air quality. Any machine that's going to generate pollution on site needs to have a permit. So when you're doing a new hospital, that would be all of your emergency generators, And basically, the air CARB reviews the equipment, looks at the level. Typically, generators have ratings for air quality, and either allows or obviously allows them to work on your site. Go ahead to the next slide, please. Building permits, and this is where OSHPD gets involved in the review and approval of designs that are submitted. As an agency, we're responsible for hospitals, skilled nursing facilities, psychiatric facilities. We review, approve, and during construction are involved in the testing and approval. The following facilities, we write the code, but we do not oversee the design or the construction on these. That's clinics and correctional treatment facilities. Next slide, please. In California, the healthcare building codes, I'll talk about OSHPD CAN 2, the California Administrative Code, which basically lists all of the relevant codes that come into play, the building code, seismic requirements, fire code, and electric code for safety. Next slide, please. The building codes, in general, if your microgrid is going to supplement the normal power, it's fairly straightforward to get a design submitted and permitted to do that. What we've been investigating and looking at is what are the possibilities and what would it take to get a microgrid to supplement the emergency power. In this case, it becomes much more detailed. The equipment needs to meet special seismic certification. You need 72 hours worth of on-site fuel storage, and your product needs to be listed for emergency use. Next slide, please. CAN 2.0 from OSHPD requires local agency sign-offs. Typically, with a microgrid, you're going to be installing equipment on site that will have a visual appearance that needs to be approved by local planning zoning. It'll have requirements that the local fire authority is going to need to look at and make sure that it's a safe installation. The air quality that we talked about, permitting for underground fuel storage, and all of that is in CAN 2, and that would be something that OSHPD would require is signed off by other agencies before a permit can be provided. Next slide, please. The CEC, California Electric Code, California Fire Code, Nfpa codes specifically address healthcare facilities and requirements. They address the distributed energy resources, have requirements for engines, generators, turbines, stationary storage batteries, photovoltaics, and the requirement for emergency and standby power requirements for hospitals. Next slide. The good news, permitting for microgrids is achievable for OSHPD, for California healthcare facilities. We already have dozens of projects that have been built with fuel cells or PVs installed to supplement the utility service. To date, no microgrids have been installed as emergency power systems, but we see that the codes are trending in that to allow that to happen. Next slide. Remember, we talked about the benefits of the microgrid: increased power, lower environmental impact, lower energy costs, potentially high power quality. This added benefit of using the microgrid for the emergency source obviously has high environmental impacts. It also has high initial cost of impacts. Next slide, please. So how do we, this whole white paper that I worked on, a lot of the emphasis was try to work out how microgrids can be implemented for OSHPD facilities. As a number one marching order, we know that a microgrid, if it's used for the emergency power source, is going to have to be every bit as reliable as the current gold standard, which is emergency diesel generators. We talked about the special seismic certification requirement. just like the generators, if you're using a microgrid, it's going to need to be able to continue to operate after a seismic event. The equipment and controls would need to be listed for emergency power. There will need to be a requirement for 72 hours of on-site fuel storage, and in general, we'll have to meet code. Next slide, please. Current codes. The microgrids is starting to show up in current codes. In 2017 CEC, which is based on the National Electrical Code, Article 705 introduces interconnected electric power, which is essentially microgrids that would parallel with the normal power service. 517 lists fuel cells as acceptable emergency power sources. Nfpa 99 lists battery systems and fuel cells as acceptable emergency power sources. Nfpa 110, not much mentioned in the microgrids or fuel cells. Next slide. Here I show a microgrid implementation flowchart, and essentially it is quite small, but this is a flowchart that basically says what type of OSHPD facility are you building. If you're building a hospital, you have a yes/no option. If you follow over to the yes portion, you have an option. Are you planning on using your microgrid for normal power or emergency power? If you're using it for normal power, you'll see on the left-hand side a column. There's about 10 codes that you would need to comply with. If you're using it for emergency power, there's roughly twice as many code requirements. And I encourage you to take a look at the link at the end of this presentation. You'll be able to see this in real size, but it's meant to be a tool to implement microgrids. And next slide. Again, when we talked about all of these codes, I've highlighted three, and I started to talk about them. One is this California Electric Code. The other is the NFPA 99 Healthcare Facilities Code, and the third is NFPA 110 Emergency Power Code, Emergency and Standby Power. These are the three codes that are most relevant on the discussion of microgrid. And these are the codes that are continuing to evolve. If we can go to the next slide, please. What's exciting is that these codes are evolving, and they are recognizing microgrids as an acceptable source for emergency power. In 2017, we saw that the National Electric Code, now this is NFPA 70. California uses the California Electric Code, which has our California amendments. But in 2017, it first introduced the term microgrid. In 2020, which has not been adopted yet, it will include a definition for the healthcare microgrid and will identify microgrids as an acceptable source for either normal or emergency power. Next slide, please. NFPA 99 Healthcare Facilities Code, again, in 2021, which would be adopted in 2023 in the state of California, that code will introduce the term healthcare microgrids as an acceptable source for emergency power. It includes a statement in this new code that's yet to be adopted, is that shall be designed with sufficient reliability to provide effective facility operation consistent with the facility operations plan. So, in different than what we see for emergency generators, which is very prescriptive, this has a requirement that it becomes reliable, and we have some work to do to define what that reliability is. Essentially, at OSHPD, we're looking at that to mean just as reliable as the diesel generators that we see that are currently installed in all of our hospitals in California. Next. NFPA 110 the third code that we did a deep dive on, it's still written in the terms of emergency generators as power source. No mention of the microgrid. I'd expect there'd be some changes coming. There's been an effort to align these three codes, which all talk about hospitals' emergency power requirements, so that they would all align. And it looks like they're all trending in the allowing microgrids for emergency power sources. Next slide, please. One thing that I need to point out is that it is quite possible that you could have a design that is totally code compliant, permitted, built, operational. But at this time, the Center for CMS, Center for Medicare and Medicaid Services, requires that you have emergency generators for your emergency power source to get reimbursed by the federal agency. This is because they adopted 2012 version of the Nfpa 101 and 99, which do not recognize microgrids as an acceptable source. So there's a little work to be done here. Obviously, every hospital in the state of California is going to be pursuing these federal rebates. Next slide, please. So, microgrids as emergency power source. What's the path forward? We did a deep, as the white paper was written, we did a deep dive analysis on these three codes we talked about: Nfpa 70, Nfpa 99, Nfpa 110. We've made recommendations about how these could be aligned to be consistent with allowing microgrids as an emergency power source. Right now, there is a void that needs to be filled as far as manufacturers that have products that are shaker table tested. That means that they could still operate after a seismic event. And that will that's going to be a requirement to be able to have product that's available to use. UL has been developing more current microgrid controller listings. The microgrid has it basically directs traffic. It directs the flow of energy. They've been developing advances listings for microgrid controllers. And then finally, memorandums could be developed and forwarded to CMS to allow other emergency power sources so that you could get your reimbursements from the federal government. Next slide, please. This concludes my presentation. You'll see at the bottom a link that would get you into the white paper we put together. I recommend, if you're interested, to take a look at that. There's a lot of good information there. Thank you.